All right, so this is finishing up the Chapter 4, Objective 5 lesson on our integrals. So I realize this is an indefinite integral, but we will actually be working with the definite integral of composite functions, and then just also looking at other forms of it as well. Okay, so that would be the definite integral. Okay, so change of variables for definite integrals. So if we have a function, we'll let u equal g of x, so some function in terms of x, and it has a continuous derivative on the closed interval from a to b, so these will be our lower and upper limits. And as long as our function is continuous on that range of g, then we have our composite function here, right? So f of g of x, and then times the derivative, so this is our chain rule piece. And then this will equal, so we'll do at some point, right, we're going to let u equal g of x. So if u is equal to g of x, then our lower limit is going to have to change with it, as well as our upper limit will have to change with it, right? So that when we're in this format right here, these will be values of x, right? So at x equals, say, 2 and x equals 5, we will have to change that over here to where u is equal, right? And then u is equal, because we will be in terms of u. So u will equal some number here other than whatever number was there, right? So we'll have to change those limits. Okay, so not that you have to, but you will be expected to when we get into kind of our multiple choice questions, making sure you understand that concept, that the values of the limits should change as your variable changes, right? So if this is in terms of x over here, these will be values of x, and if this is in terms of u over here, this should be in values of u. Okay, so our limit should change along with our variables. Okay, so let's go ahead and take a look at this first problem. So we want to integrate just like we already know how to do. So when I look at this piece right here, we're going to say, okay, is that in the right format? And it is. And then we would do our u and our du substitution. So we would let u equal the inside component here, which would be 3x plus 1. And then we would take that derivative, so that derivative would be 3, and then multiply that dx over, right? So if I look here, I have a replacement for 3x plus 1. I will replace it with u, and it will stay as squared. And then right here, I need a replacement for dx, so I'm going to divide that 3 over. So then I would have 1/3 du is equal to dx. Okay. So I'm going to pull that 1/3 to the front, and then this will be du. So now this is the new component. So right now I have limits of 2 and 4, right? So limits of 2 and 4. And these are values of x, right? So x is equal to 2, x is equal to 4. So I have variables of u, so that means this cannot be a 2, this cannot be a 4, because that would imply that these are, x and u is the same, which it isn't. So if I know x is equal to 2, my job is to figure out, well, what would u equal when x is equal to 2? Okay, so in order to change my limits to align with the variables, I need to substitute my limit values, right? Into whatever I let u equal. Right? So in this particular problem, u is 3x plus 1. So then when I know x is equal to 2, right, so up here x is equal to 2, so when I substitute that in, I will get 3 times 2 plus 1, so then my new lower limit will be 7, okay? So one more time, so at x equals 2, I would get u equals 3 times 2 plus 1. And then I'm going to do that the same for my upper limit, so x is equal to 4, so that would be 3 times 4, which is 12, plus 1, which is 13. Okay? And so again, I'm just replacing that upper limit into my expression for u. Okay, and then from there, I just integrate just like I normally would. So I'm going to increase the power by 1, and then divide by the new power, and then my limits are from 7 to 13. Okay, and then I'm going to pull that other 3 out, so that would be 1/9. And then I have u cubed from 7 to 13. And then we're going to substitute in the 13 and the 7. And I feel like I probably could have picked smaller numbers, but we're going to work with what I did. So that would be 13 to the 3rd, and then minus 7 to the 3rd. And then I'm just going to leave it like that. Okay, and then that would be my answer, and that's it. Okay, so let's go ahead and do the next one. So we're going to take a look at this one. So if you feel pretty good about it, you should go ahead and try this one on your own. Okay, pause, forward on. So I'm going to just start with the rewrite though. So I'm going to move both of these up to the numerator. So I have 1 plus the square root of x to the negative 2 power, and then x to the negative 1/2 power. Okay, so that's what I have. And so then I'm going to let u equal this quantity here, and I'm going to do that up to this side here. So that would be 1 plus root x, or x to the 1/2, and then take that derivative. So that would be 1/2 x to the negative 1/2, and then multiply the dx over. So I'm going to go ahead and replace the 1 plus root x with u, so that would be u to the negative 2 power. And then right here, so these are pretty close to being the same, but not quite. So I'm going to multiply the 2 over to the other side, so that would be 2 du. So then both x to the negative 1/2 and dx will be replaced with 2 and du. And then I need to change my limits as well, right? So let's go ahead and do that. So x is equal to 1, so I'm going to go up here into terms of u. And I'm going to replace both 1 and 9 in for x. So then 1 here, so 1 to the 1/2 power, or the square root of 1 is 1. And then plus 1 more is 2. And then I'm going to do the same thing for the 9. So that would be 9 to the 1/2 power, which is the square root of 9, which is 3, and then plus 1 is 4. Okay, so again, all I did was take the 1 and the 9, replace it for x, and then solve for u. Okay, so then let's do a little rewrite and power rule. So I'm going to pull that 2 out to the front. And then I'm going to add 1 to the power and divide by the new power. So that would be u to the negative 1 divided by negative 1. And then again, I have that 2 there. And then I'm going from 2 to 4. So I'm going to divide out that negative 1. So that would be negative 2. And then 1 over u. And again, from 2 to 4. Substitute in the 4. So that will give me 1/4. And then minus, and then substitute in the 2. Okay, and feel free to simplify that, but I'm going to leave it just like that. Okay? All right, and then this next one is a multiple choice, so if you're feeling pretty good, give it a whirl, see what you can come up with, and check for your answers. Okay? All right, so this one right here, so we're going to let u equal 2x plus 1, and they want to know which of these is the correct substitution step. So right off the bat, I can see that my x is 1 and 4, and so then I know anything that has a 1 and a 4 in it as my limits probably is not right. Because why would the limits of x be the same as the limits for u, right? It should change. And so let's go ahead and check those and make sure that the 3 and the 9 are correct. Hopefully they are. So when x is equal to 1, 2 plus 1 is 3, so that would be my lower limit. When x is equal to 4, that would be 8 plus 1, which is 9. So I know it's either d or e at this point. So now I'm trying to decide, okay, should I have, divided by 2 or multiplied by 2 to get those two functions to kind of line up? So if my u is 2x plus 1, when I go to take that derivative, that would give me a 2 and then multiply that dx over. So if I look up here, I need it to be just a dx, so I would divide by 2, right? So it should be a 1/2 du, so it should be a 1/2 out front. Okay? All right. And so pretty easy, yeah? So then now for the last part, this is just kind of an application component. Well, it's kind of leading into an application component of the fundamental theorem of calculus. And so this is kind of an extension of our previous objective, and then kind of applying that a little bit. So this is our first fundamental theorem of calculus, right? So let's take a look at notation. So lowercase f, right, is our derivative, and then capital F is our antiderivative. So this is that first fundamental theorem of calculus, right? And then this is just a modification of that, right? So all I did here was I added the f of a over, right? So f of a. And so these are equivalent, right, equations. Just this is solved for f of b, and this is solved for the integral. So oftentimes what we will be using this for is we know that f of a is my lower limit evaluated, right, into the original function. And then this is, you know, the integral component. So its application where it's going to head to is this is like our starting amount or our initial amount. And then this is our change in the amount. Okay, because why do I know it's a change? Because this is like a delta y, delta x, right? So f of b minus f of a, right? And that's what this is equal to. So f of b minus f of a, so like x2 minus x1, or like a delta x value, right? So that's a change in value, okay? So what we started with plus our changing amount, which will give us our final amount. Okay, so that's what all of that is about. Okay, so that's just kind of leading into trying to understand, like, what is this integration thing besides area? So this right here, because that's equal to a delta x or delta y value, delta f value, so this is a changing amount, right? And then f is our antiderivative, so going back to the original function. And so these are like kind of that delta y component. And so our final amount, our ending amount, where we evaluate at x equals b, and then this is equal to our starting amount, whatever that is, plus that change in value. And then the piece below it is just the same thing, it's just using different notation. So instead of using lowercase f to say derivative, what if we actually, shocking, use f prime, right? Because we know that to mean derivative. So if we use that as f prime, then this would stay in lowercase, right? So f of b minus f of a. So that would be kind of our delta y values. And so these are just equivalent, right? Just using different notation. Okay, so let's go ahead and take a look at this particular problem. So we're trying to apply like this information up here. So they're saying that capital F of 2, or excuse me, let me read the whole question. So find the integral expression. So they're wanting something that looks like that for the following. So they're telling you that here we go, we have this f of 2 amount, right? We want to figure out what is that. If f of x is the antiderivative for lowercase f of x, and f of 0 is equal to 3, okay? So we have to like be thinking about, you know, like what is that information that they're giving us, right? What is that information they're giving us? So we have our values here of a and b, right? So we have like, this is like our a value, our starting amount, and this is our b value, okay? And we're trying to put it into like this format right here. So we're trying to figure out what is f of 2, right? So what is f of 2? So that's like our f of b, right? And so that is equal to f of a, so in this case f of a is 3, so that's equal to 3, plus the change in the amount, and we started at x equals 0 and ended at x equals 2, okay, of our function, whatever that happens to be. So then that would be our integral expression, right? So our starting amount, our starting value was we started at 3, and then we're going to make some sort of change, we don't know what that is, from 0 to 2, okay? And so keeping in mind that this was at x equals 0, right? At x equals 0, and my lower limit is 0 as well, okay? All right, so let's take a look at the next one. So same concept here, okay? So we want to find g of 2 this time, so g of 2. So here we're starting at 6, right? A little strange here, starting at 6 and we're headed to 2. So we're at x equals 6 and we're headed to 2. So we're going to be going backwards here. So we started at 6, which is -5, right? And then our change in our amount. So this came from x equaling 6, and then we're headed to x equaling 2. of g of x, and then dx, okay? All right, so we are going backwards here, right? So if this is like, oh, this is strange, there's a 6 here, there's a 2 here. The other way we can think about this, right? So this is an alternate way to kind of write that same thing, is instead of saying, you know, from 6 to 2, keeping in mind we're going backwards, is we can say, okay, so we're going the opposite direction of 2 to 6. And so that would be an acceptable way to do that as well. Okay, so if this is a little uncomfortable that the smaller number is up here instead of down here, is we would just, you know, invert those limits. So instead of saying going from 2 to 6, or instead of saying 6 to 2, which is backwards, we're just going to say opposite of, right? So leftwards, and then 2 to 6. Okay? All right. And then let's do a picture example, a couple of them. All right, so for this one right here, so we want to find the value of f of 4. And we know that f of negative 4 is equal to 1. And then this is a graph of our f prime. And it is a semicircle with radius 4. So let me mark all of those values. And then the derivative of f is shown in the figure to the right, so f prime. So we're going to step our integral expression first. So we want to find f of 4. And then that's equal to my starting position, which was at x equals negative 4, so starting here. And that value was 1. And then we want to add to that the change in position. So that was, we started at negative 4, and we're headed to 4 of f prime of x. Okay? So that's the integral expression. Now we actually have to calculate this and go a little bit further because he gave us this graph, so we should be able to figure this out. So what they're asking here is then we're going from negative 4 to 4 of f prime, which represents the area under the curve. So we know how to find the area of a semicircle. That would be 1/2 pi r squared. And then I know my radius is equal to 4, so that would be 1/2 pi times 4 squared. So then f of 4 would be equal to 1 plus 1/2 pi, and then 4 squared is 16, right? And so half of 16 would be 8, so that would be 1 plus 8 pi. Okay? All right, last one here, last one. All right, so for example 5, so you might want to press pause and give it a whirl, right? So it's just like example 4. So they're asking you for finding the value of f of 0 if f of 4 is equal to 80, right? So we want to find f of 0. Our starting position is at f of 4, which is 80. So we started at 80. And then we're starting at 4, and we're headed to 0, right? Starting at 4, headed to 0 of f prime of x dx. Okay, so again, this is backwards though, right? So we're starting at 4, headed to 0, so we're headed leftwards. So we're going to flip that around, right, to have it make a little more sense. So we have 80 and then minus, and then we're going to go from 0 to 4. Okay. All right, so from 0 to 4 of f prime, and this is our derivative graph. So that means we need to find the area under the curve. So if I'm going to chunk this up into like this little bit right here. So this has a base of 3 and a height of 15. So this would be 3 times 15. So this section in here would be 45. And then let's go ahead and split this. So that would be a section of 5. As well as this one, it would be 5. Okay, so then now I just need to do my triangle. So we'll do this triangle here first. So 1/2 the base, which is 1, and then the height is 5 to 15, so a height of 10. So that section would be half of 10, which is also 5. Okay, and then this last one here, so I'm going to make a strong assumption this is in the middle. I probably should have clarified that a little bit, but we're going to call this right here at the halfway mark. So then this triangle up here would be 1/2, and then the base would be from 3 to 3.5, so 1/2 of half. And then the height would be 5, 10 would be 10 as well. So that would be 10 over 4, right? So we have 80 minus, and then let's add all this up. So that's 5, 10, 55, 60 plus, let me do a little dividing here. So it'd be 5 halves, so 2.5. There we go. Okay. And so then finally, let's see what we got. So 80 minus 60, that would be 20. And then minus another 2.5, so that would be something, 17.5. Okay, so then they're asking for indicate the units of measure. So when I found each of these areas, I was multiplying miles per hour times hours, right? So I was doing miles per hour, and then I was multiplying that by an hour, so that would cancel, right? So then that would be 17.5 miles. And then what is that final value representing? So that would be representing at x equals 0, right? Or t equals 0 perhaps would be better. So at time 0 hours, my location was 17.5 miles, right? So at t equals 0, my location was at 17.5 miles. And then 4 hours later, I was at 80 miles. Okay? All right, and that is it.